Oh, wow. That was a nice start. Great for this talk, because we're going to do a little science fiction thing, but it's actually in the reality of Java. So guys, girls, welcome. Actually, everyone, welcome to writing GPU-ready AI models in pure Java. And we're going to be helped by a few things that you already know in Java, but also by Project Babylon. So without further ado, Lise, we need to put together and explain a bit some parts of our title, because it's very complicated. Can you please tell the people what
When we were putting together this talk, we've been very confused ourselves too a couple of times, and that's why we want to help you understand this with some anti-confusion charts. So here is one explaining CPU. That's the one we run Java on normally thanks to the JVM, and that has a couple of cores that can do very powerful things. And so typically when a program is run, typically in one of these cores, it's going to load an instruction, maybe load some data, do the operation, write the output to a register or somewhere else, and then it's going to load the next instruction that can actually use the output of the former instruction. That's how it typically goes, and so on and so on. And typically on different cores, we have either different threads running or different programs all together. Now GPU, graphical processing unit, that's something very different. That has many very complicated, very easy cores, that can do many things in parallel. And they're typically used for SIMD operation, single instruction, multiple data. So the same small piece of instruction or code is run on many different data inputs at the same time, which we will usually call vectors or matrices, which are two-dimensional vectors, or tensors, which is like even more dimensions. CU, that's just for people that are too lazy to type bye-bye out long, and CU like cuprom, that's just a metal. So now we have that confusion out of the way. Why would we want to talk to this GPU, which normally we don't do directly in Java, but what this talk is all about nonetheless? We have massive parallelism that's possible. So instead of waiting on the output of the former calculation, you just do them all in parallel. That only works when your next instruction is not depending on the former one, so when you can actually execute everything in parallel. But in that case, it of course goes much faster. And also, interestingly, GPUs, they are not this very complicated Swiss pocket knife that can do many things like a complex CPU core. They're much simpler, and therefore they will also use often less resources to do the same things when they can be done in parallel, because they're easier layout, and they're also made for loading big amounts of data in parallel to all of these cores. Why would we want to use GPUs for AI? Because many AI algorithms have a lot of optional possible parallelism in there with mainly matrix multiplications. So here, for example, you see a fully connected neural network. And do I have a kind of point?
Yeah, it works.
Wait, yeah, tell me. Sorry.
This one. Tell me what, yeah. We want to show the neural network, yeah.
Complicated.
Work? Oh yeah, it works now.
Yes. Amazing.
Magic.
Okay, thank you. So I have this very
and no
big,
AI yet.
but here in the middle of it, that's the node I want to be talking about. Like to calculate the value of this one, we will need all the input values multiplied by the weight. Like so, from the first one to the first one, there's a weight. From the second one to the first one, there's a weight, and so on and so on. And as you can see, all these calculations here, can be done in parallel because none depends on the other. They depend on whatever was in this former layer and the weights. The same goes for that second node. Like the first node doesn't have to be done calculating to start the second one because, again, it's independent. And that's why you can have many operations done in parallel here. And it would take, as you can see, much longer to do so sequentially on the CPU. Now, to conceptualize what it takes to run something on the GPU, let's look how it usually goes for running something on the CPU, which we Java developers are somehow way more familiar with. So we type our source code in Java, for example. Then this is translated by the compiler into bytecode, which we're going to say is an intermediate representation. You can put this bytecode on any type of hardware provided there's a JVM that can translate from this bytecode to your specific hardware. And the people at the JVM team, they put a lot of effort in making sure that this bytecode can run on almost anything. This JVM is then going to translate it into machine code, which can turn on your specific CPU, right? Because there it becomes specific on your laptop or CPU model. Then for GPU, it's a little different, but very similar nonetheless. You're going to write your source code in typically a programming paradigm that's parallel friendly. So you're going to already write your code a bit in a parallel way. For example, in CUDA-C, when you would want to steer NVIDIA hardware. But there's more languages depending on which hardware provider. That gets translated to also an intermediate representation. In NVIDIA's case, that's PTX. So that is parallel thread execution. That is sent into a runtime or driver that translated to machine code for the specific hardware backend. And that is then run on your GPU with massive parallelism. So when we will be talking a bit about front end here, we're going to be meaning the code that we write, and the back end is really the piece of hardware. So why is it so complicated to support GPU access directly in Java? Since we already do it for CPU access for multiple vendors, why not just do it for GPU? Well, it's because there's less different CPU architectures that we have to support than GPU. So here's just a short list of things, of different hardware vendors, but there's many more, and they all come with their own intermediate representation and own hardware, so it's much more work, but we are trying nonetheless, and Anna is going to talk more about that at the end. So who are we?
Well, because I, for one, don't like that much, and I don't know about you, Lise, but me and C++ in high school and university were not getting along, and I love Java because I don't have to allocate memory or think about the allocation of memory. We are here today talking about how to use Java, and mainly because we're part of the Java platform group. We're working as developer advocates for Oracle, and we're closely working with the team that is building Babylon, but we are also aiming to contribute part of our demos today to the main repo as well. So you're actually the prime audience of what they are going to experience soon in a more neatly coded way, because probably we're going to get some review on our PR and we're going to change a few things. So I am Anna. I'm currently working as a developer advocate in the Java team at Oracle. I'm passionate about performance, about JDK tools. We have both in a certain way today. JAxtract and, well, Java in general. So, and today we're going to run things on the GPU, definitely. And together with me is Lise, my colleague, my new colleague, which I'm excited to have as colleague, all about AI.
Yes, exactly. So I started at Oracle 1.5 months ago. This is my... It's not
second.
Even, it's already my second, forget it.
Yeah, close to second month.
Yes. Yeah, and so I was hired specifically to help the Java and AI ecosystem, which is a tremendous job. I'm very happy with that because I'm also working on LangChain4j, but I love this whole AI ecosystem, and this is another aspect of it, talking to your GPU.
So what are we going to use today to talk about this?
What are we going to use?
Well, the deep learning models. You've been telling me like a lot that you've tried, so go ahead.
Yes.
Introduce people.
Exactly. What are we going to run on the GPU today? I will start with showing a deep learning model. We're going to show other stuff later too. So before we're going to run a model on the GPU via Java, let's have a look what is in such a model. So a model, in the end, is nothing more than a program. You send something in, be it an image or be it a text, and what comes out is a classification, a next word, a completion. So model, basically big calculation. And the way they are typically stored is with a graph, a calculation graph that we have to run through with operations and layers defined in there. We'll look later into more concretely what is literally in these models. And so next to a calculation algorithm, we also have the weights, and there are many, as you could already see before. That didn't seem like a very big network, but there were already very many weights in there. And they're typically stored differently. And then together, you put those together, and you can run this calculation on an input. You get an output. There's different model formats. So .pt can get executed by PyTorch, .pb by TensorFlow runtime, .ONNX by the ONNX runtime, and so on. So what we will need with a model is a runtime that supports it, that can load this model and execute it and run it on your hardware. So that runtime is really going to take care of talking to your GPU mostly. Now, we are going to look at an ONNX model, and we need an anti-confusion chart here again, because I know the first thing you're all thinking of when we say ONNX is this Pokemon. But in this case, it's Open Neural Network Exchange, and that's an attempt to standardize and exchange models currently maintained by Microsoft. It's both a format, so we have .ONNX files, as a runtime that they provide, so you can run these .ONNX files on your GPU. So ONNX is also kind of gemstone, a Pokemon, and then important, since we are in Flanders here, when they say ONNX, then don't be nerd-sniped. They will probably not want to talk about neural networks. They just mean, oh, nothing.
Like, I hear that quite often in the Netherlands as well, so it's fine. Especially when people apologize. Oh,
so are you disappointed now? You're talking, everybody's talking about
ONNX
here.
Yeah, okay.
But no. All right. So what's in the ONNX runtime? That's the whole blue part here. A way to load an ONNX model, to load the input data. We are going to look at a facial emotion recognition model. So our input data will be a vector version of an image. And then it does some kind of transformation, puts everything together. And in the end, at the bottom, you see the execution providers. So ONNX runtime can talk to your CPU or to GPU or to other things like
FPGAs, I think. And,
yes,
and
exactly.
NPUs. So different types of architectures. We can call them heterogeneous devices, all these kind of devices that can support parallel computing.
Exactly. This other reason it's really hard to just support all GPUs is that there's also NPUs, which are derivatives of GPUs, called neural processing units, LPUs, I think, TPUs, sensor processing. So there's so many, and that's why it's actually nice to have such a runtime sitting in the middle. So the first demo, we're just going to try to use this runtime from Java. But what does Java know about ONNX? Actually, absolutely nothing. So for Java, the ONNX runtime, we don't know about it. We consider it a foreign native library. And that may already ring a bell. We have Project Panama's foreign function and memory API that does just that, allows us to talk from Java via bindings to native runtimes or native libraries. That's what we're going to do here. But also the ONNX format is also foreign to Java, so we say it's a foreign programming model.
So
and
we're going to look into how to can appropriate that in Java as well. But let's start simple, right?
Yeah, we will just start with trying to get that ONNX runtime running in Java. So the way we're going to do this is that we create bindings for whatever is in this runtime. This runtime is a program, like it's a dial-up on Mac, for example. And they're typically also come with a C header file that describes all the functions that are present in there, for which we can provide a Java binding. Now, we're not going to do that by hand. We have a tool called JExtract.
JExtract. And we worked on this demo and we got only the essentials. So pretty much we thought of like extracting the API of the runtime, because we're going to always need the API of the runtime, and the provider, GPU, because we saw that ONNX can connect to multiple providers. This talk is about GPU, and we want to run it on GPU.
Yes.
So.
Yeah, we first just run it on ONNX runtime, and we were very happy. And then we figured out that it just ONNX runtime talks to our CPU, which defies the point. So we made some extra bindings to make sure this thing works with an execution provider called CoreML that will be able to talk to your Mac GPU. But again, this execution provider depends on your actual hardware. Good. I think we're ready to look into the code.
Now we pray a little bit to the demo gods and first to switching the HDMI.
I don't hear enough prayers.
Please, please, please.
Guys, we need more prayers.
It works.
Thank you, thank you.
Okay, let me do this and be the standing human.
This is not looking good
What?
at all. This turning spinning wheel here. Shall we swap back to yours?
Oh my God. Okay. It's good. Thanks.
Yeah, they've not been praying enough.
Okay. Let's go
Yeah,
back to
we
me.
switched because I have a different keyboard layout. I will survive.
I have the international keyboard layout. So you're lucky. I was somewhere else, but doesn't matter. You're gonna mess up things a bit for me, but I hope people don't mind. Okay, getting back.
Okay, so we are gonna use a called FER, F-E-R, facial emotion recognition model that we found on the ONNX model repository on GitHub. There are many, many, many models there that you can play around with. It's only 35 megabytes big, and we can so run it locally pretty easily.
Yeah, and we stored it in the resources folder like any good dev does when they want to have something successful running. We just put everything in resources.
I'm very sad because I had all these memes uploaded. This is really sad. Anyway, we will.
That was the fun part with the meme.
Right? Oh man.
Okay, let me get the Mac.
Maybe you can revive
I
my
have the
Mac
magic
while I
touch
show
with
the
the
code.
Macs.
Thank you. I will unlock it for you.
Thanks.
I think you'll have to kill it and restart it. Sorry for that.
Yes.
Okay, so let's have a look. This code is part of Babylon. We will share the link, or we have already shared the link.
It was already in the slide.
We'll show it again. So you can try this at home if you want. The thing I explained with JExtract generates bindings that live here. They look a bit weird, like this ONNX Runtime C API. See if I can zoom. I can. That's very positive. It's it's always interesting to.
Or you can direct me to.
I'm fine. Yes. Okay. So as you can see, this says generated by JExtract. We didn't do this, and also you don't have to do this at home. We already created these bindings. If you want to have fun, you can do this, but you can also use the ones we've already created for you. We a part, and our colleagues at Oracle another part of them, and they basically map anything. Structs, objects, methods from the ONNX runtime to Java. Now, our colleagues made a nice wrapper around it called this ONNX runtime that just distills the things we really need and wraps it into methods that are easy to work with, which I will show you in a minute how it's done. They also made this tensor object. It's also a nice wrapper, which you also can use at home. You don't have to do this work again.
Yeah, but we didn't want to read that much code as they worked on, because they worked a lot on it. So we made our own ONNX runtime just with FFM and just to double check things, just for the demo purposes. And that's FFM only.
I think we do also like to really get our hands dirty on the most basic level to make sure we know what we're talking about.
That's also.
Or we were silly.
I have your.
You have it working again?
Yes, I have.
Let's give this a try.
Because she has all the memes and all the good and all the good emotions. That's.
I didn't want to push all those memes to GitHub repository because that wouldn't fly.
Yeah.
I want to hear more prayers this time.
Come on.
There we go. Thanks. It's oh my god.
It works. It works.
No, I have the spinning wheel again.
Oh.
This is
weird.
So
I think
sad.
I know why it happens. I know why it happens.
We give up.
You give up.
We give up.
Come on, come.
It's too bad.
I know why it happens.
No memes for
I'm going to explain
today.
you afterwards.
All right.
Okay.
Good. Then we were looking. So it's in the CR examples.
Wait.
ONNX.
Wait. Yes. Now we can do it.
I think
okay, well, you didn't have a video there, so you were explaining, but people were not seeing.
Right. Okay. So we have a Swing application just because it's a nice little demo. But the core that it uses is this inference class. And I'm going to walk you through what it does. So we say our model is stored here in the resources. Anna Maria showed it just before. We say the emotions that it classifies, because funny enough, they're typically not stored inside of the model. So you have to know them next to the model to map the outputs to what they actually mean. So these are the emotions it can classify. Then we get this ONNX runtime object. It's the one I showed you before, the nice wrapper around the bindings. So we get a runtime instance of this. And then we're having this try with resources of this arena of confined. And that's gonna allocate a part of native memory, so you're outside of the scope of
The
Java's
JVM,
typical JVM memory with garbage collection. This is not it. It's really native memory that's gonna get released again, because that's important when dealing with native memory. It's gonna be released when the resources, try with resources ends. So in that piece of memory we are operating, we create a session with session options there. And we're going to enable CoreML. You can look into that code specifically because it's important to actually address our Mac GPU. That's why we need this CoreML version of the ONNX runtime, or the execution provider with it. Then we're going to read the model bytes of our ONNX model document. And we're going to create a session with this model in this place in the memory with this CoreML enabled.
So we're basically talking to the native runtime. We're just ingesting the model. We don't care about what's in the model for now. We're sending it to the runtime. We go to the functions that are in the runtime and tell it, hey, do magic for me. So let's do some magic for people here.
Yes. Okay.
It's going to be a little boring.
It's not going to be the memes. So we still need to load our image in the correct tensor format, and that's also given with the model. So this one was like dimensions 1, 1, 64, 64. So we're going to have to rescale the images so they fit as input and wrap that in such a tensor object that we saw before. And then we're ready to just run the inference in this inference arena with the input tensor, gives us the output. Then there's one more catch. The ONNX, fair ONNX model outputs logits, which is like an intermediate thing in machine learning models. When we want to interpret it, we want to actually see chances in the classification, not logits, because logits can be negative and everything. So we're going to normalize that with a softmax function that we have also in this code. So these raw logits are translated into categorization chances. Then let's run this one.
You want to use the terminal? Well, that's brave.
Yeah, I mean, as you wish. You wrote such a very nice script. So the thing is, this lives inside Project Babylon, for which you would need a custom build. Anna-Maria will explain you later, because for her part, you really need the Babylon features.
But I don't want to run a custom build of Babylon.
But for this part, you can do with Java 25 if you're just sure to. Oh yeah, if you want to set it, that's even cooler. Thank you.
Yeah, so just for everybody to be clear, I'm going to use Java 25, no magic and so on and so forth. So what I'm going to do, because this isn't a Maven project that actually needs Babylon, to be fair, and what I did, I actually compiled just those classes that are related to Java 25. So,
or to the fair demo, and not all the rest that actually needs Babylon. That's why this demo, if you use a script here that you can see, this you can do with your normal.
I ran it a couple of times, but you never know.
And yeah, so sad. We only have those faces and not the memes. So that's for now the only things we can analyze.
Let's put some faces. Just put them on like multiple times.
But yeah, well, we can see, but it's going to give the same result in the end. So now it's analyzing them. So now it's doing the actual inference on GPU, should be, and they these are very happy, and these are less happy, but still not saying sad.
Yeah, that was like it was confused. So it wasn't.
It's really not a good model, but happiness is typically classified.
It depends. Correctly. I'm coming from Eastern Europe, and for me, I express happiness usually like. So I don't know. I think the model is culturally aligned.
Happy Lisa and happy Anna.
Yes.
That's why everything's happy.
It's culturally aligned. That's what I think.
All right. How do you close this one?
Yes. Just give me a moment to go as back. You want the right slides, right?
I would still need to have a look at the code, because I want to... do we see the output of this run or not?
Yeah.
The logs are...
Oh, no, that's the other part. Where do you have it?
Logs.
Yes,
yes. I would just want to show you, we had enabled logging, and just...
it's not a French keyboard.
But it's correctly typed. Oh yeah, this Control F is...
It's not feeling it.
It's not finding it, but okay. At least on my computer.
Yes.
If you search for, it's somewhere saying there, all nodes are mapped to CoreML execution provider. which, still important to note, is not a guarantee that it will run on GPU, because this core ML execution provider will still decide itself based on the code it gets if it's better to send it to CPU or GPU. But if you use big parallelism, it's for sure gonna route it to your GPU. That looks good, right?
Yes, it's Core ML. It's saying that you're using 32 number of nodes supported by Core ML, so it's pretty much going to Core ML.
At some point, it says that it maps all the nodes there. So
yeah, I mean, I'm happy with what you did here. It was a very good start. I mean, it was a good thing.
Yeah, but for now, the model itself was still ONNX format. So Java has come in between ONNX and its runtime. We can do better, right?
Yeah, we can do better. But we need some extra help because, as you explained, well, the ONNX model is a computational graph. And I kind of put here one of the a simpler model, because the emotional model, the facial emotional recognition model, doesn't fit the slide. That's the thing. So we chose something that fits the slide. And the reason why we did it was because I want to explain a bit about it. So you have to think about ONNX model as a graph, right? And we want to represent this graph in Java. I mean, metadata is interesting, but it's more interesting, let's say, for the actual runtime. I don't think representing metadata is the issue. When we're looking at this, I think that some of us are thinking like, well, how do I do this? Do I go and represent graphs in Java like I used to do it, I don't know, when I was learning C? Not really. So what we need to think about all the time is what makes this a model. So this graph structure, the nodes are the operators, and more precise, they're called tensor operators. So in the GPU world, we're going to always work with tensors, as Lisa has shown. Earlier, the tensor was a plain Java class. It will stay a plain Java class as long as we're in Java. But when it gets to the ONNX runtime, well, that's a different story. It sees it a bit different, and we need to see how we can connect the worlds. Then we have tensors flowing in between those operations. Weights are included as constants for those tensors. So in that case, that W, that B that you see there, so those weights and biases are helping the operators, are initializing our operators with something. So the model operates, has some operations inside it, but it needs a way to initialize those operations. And of course, we need to serialize, right? You see connections between those operations. So we need to serialize those, and in ONNX, that is given by protocol buffers. We get inputs and outputs. Looks very complicated so far, but let's see how we can do better, because right now we know data types and how to represent things in Java, but what I know from Java doesn't look like this necessarily, and so I need a little extra help. And the little extra help in my case, in our case actually, was Project Babylon. What Project Babylon aims is actually to extend Java's reach to foreign programming models, like ONNX model, because they differ from our normal Java programming model. But we need to make this easy, right? I mean, I like working with FFM. It's still understandable, but there's I still feel there's like a gap. So to make it easy, what the Project Babylon did, they created the @code reflection annotation. So whenever you're writing your Java code, your method in a Java code, and you annotate that one with @code reflection, what happens at compile time, that you're helping your compiler and say, hey, this, you actually should think about it. You should reflect on it. So at compile time, the Java-C compiler reflects over the code that was annotated. It generates something that's called Java code reflection model. I simplified it here inside Java code model. That looks like that. So if you're interested in how that simple function looks like, that's how it looks like in the code reflection. So I printed that one at runtime. And then what Project Babylon is also giving, so it doesn't give you just a way to do this translation from normal Java code to a Java code reflection model. It also gives you APIs to build, to transform, to do something with the existing Java code model, and to help that translation to a foreign code model. And for example, if you're going to use something like AutoDiff, you can get like a foreign code reflection model that can even be even more lowered and be interpreted as JVM bytecode and run on the JVM. So it's pretty good as acting as a translator from the normal Java code that we all know towards the other runtimes. So in this case, what we're going to try is actually to improve what we had before in our example. So on top of what Lisa already showed, our colleagues from the Babylon team have expanded this prototype with ONNX, and they created a library with APIs that can help us to transform the models. They use, again, code reflection. So what they do, when they get the code model, the Java written part, you see at the code reflection, you lower the Java code reflection model, then you can transform that one to ONNX code reflection model. You do another transformation to ONNX protobuf, and then you get it executed on the API. So all these parts here are in our demo, are available, are public, and can be tried. The tough part is already there. So all the generators and all the translation part is there. So let's see what is actually this. So this is a pure Java ONNX engine, written nicely by very smart people that have created for us the operators that ONNX can understand. And those operators are going to help us to write that intermediate representation that is helping the provider further to work with what we're giving in the model, right? We're always going to work with tensors and with the different types. We're going to have more transformations and runtime. We're not going to dive very deep into that one. But we needed an example. And because the facial expression recognition, oh my God, there's too many words.
Yeah, it's FAIR.
The FAIR model was a little bit complex for this situation. We used MNIST, which is a standard model for classifying handwritten letters. It's a very known model in machine learning classes, for example, and it's pretty much used by everybody, including by ONNX in its reference documentation. So we wanted to use that one and to see if my handwritten digits are recognized by machine. Okay, so let's run the Java model on the ONNX runtime. But I need to show you how the model is created, right? So now this is fun.
So if I understand well, and it loads, we're going to translate Java code via this code reflection annotation to some intermediate representation that can then be picked up by the ONNX runtime. Basically, there's a lot of translation happening.
Yes. So we're not going to care about this part because smart people created for us. We're going to care about the model, right? So I'm going to go to MNIST. I'm going to go to model, make this a little bit bigger, and explain a bit. Now I have the ONNX model, that simple ONNX model that everybody saw. That's easier. Okay, I can make it bigger.
There's this nice Netron.app. If ever you have like an ONNX or any other type of model file, you can just upload it there and see what's inside.
Or you can install it on your computer. That's what other people are doing. By default, it's going to be open by that. So you can install it, but I didn't install it today. So, as I said, what I need for my model to work in Java, first I need to specify some initializers, right? The weights and the biases. And typically those initializers, the weights and the biases, are being stored in files. That's what I'm doing here as well. When I am constructing my model, constructor, normal Java constructor, yes. I'm just going to load these weights and biases from some existing files on my machine. And of course, you're going to wonder, like, hey, but how do you know what values to give there and so on? Well, it's a well-known MNIST data set, so pretty much the values are taken from there. Now, this initialization, then I need to go and work with each tensor operator and go with these parts that are constants to my operations and operate with them. And again, because our colleagues have generated those operators for us, and you can use other models as well to work with it, well, we have that all done in a method that's called CNN, Convolutional Neural Network. And what great people did, you can look here at this very nice graph and say, hey, div. Okay, so I need to start with my input with a div. So there's a div, there's a way to look at the modules, and then I can say, hey, div, of course, my input image, and it's a constant, right?
And div itself is offered by these kind of code bindings.
Yes, yes. So it's already created by us. It's an operator generated. They're all generated by us, so by our colleagues, actually. Yeah. They're generated by our colleagues. So you can reuse these conv, this CNN, and so on with other combination of tensor of, with other combination of weights and biases, like for more complicated MNIST models. But we like this one because it's quite straightforward and serialized. Then we have ReLU, okay. So, and we can see here that there was like conv here. We have a conv correspondence, and then ReLU gets gets what happened in conv as the next step. So everything's like really well serialized, and that's how you can write such a model in a very Java-friendly way with the existing like prototype that we have there, and get a prediction. And again, we're using that softmax layer that you said because we need it for our images. That's pretty much needed when you work with images in ONNX.
Classification altogether, yeah.
Yeah. But machine learning means you get an input. There's a model that was trained on a data set, and it does something. What it does, it classifies. It says something about that input. And you want to see that, well, it takes a decision and knows something, it can put that in a specific bucket. So, of course, we have a classify function for that. That's, again, like in the case of Lise's demo, it uses FFM API to contain all this foreign memory working over there. Now, at compile time, what happens is that the CNN with code reflection is going to be transformed for us in the foreign language, in the foreign code model, which is going to be the ONNX. So, then we have some UI. Let me make this bigger. Now I can make it bigger. And we also have like a small UI done, just because I need to like handwrite this. So how to run the demo? First, let me go to edit configurations and make this bigger and so on. No, I don't want to worry. Damn this demo. Sorry, that's good. What I need to run this with is a Babylon build. So Babylon is a project that is not, that its features are not part yet of the JDK, but is following the main line. So it can be built like a normal JDK. There are instructions over there. It's not that difficult. We can do it even after this talk and show it to you how it works. Good. So then we have to like add the modules that are still not ready to be part of the main JDK. And of course, we're going to debug a bit the result of this. But the rest is pretty much like running a straightforward Java program, but with a translator in between. So let's run it. OK. Great. So now I need to like classify and write digits. And I'm not good at writing things. So, OK. Pray for me for this to be recognized. I'm trying to do a 7. Oh, man.
Sorry.
Yeah, because somebody forgot the mouse. That's why, meaning me, I forgot the mouse.
Wow.
OK, so I kind of thought that this is a bad 7. OK, let me see if I'm luckier with another one. I feel lucky. That's like a casino thing. Let's pull another one. Let's see. I feel lucky. Uh-oh. Let's see for this one. This model is like very simplified, so it has issues when recognizing 8s.
Should I try it on your touchpad?
Yes, you try it.
I didn't run into these problems. I can do.
Oh, yeah, that one is connected. I don't. Oh my God.
All right. That's 3. Okay, she did better. I give it back to you. No.
Okay.
The thing is, this model, if you will play around with it, there's like 1, if you don't put a little extra, it will recognize it well, 4 and 7, and the rest it will mess up. So it's not all our fault.
It's not our fault. Yeah, the thing is that we tweaked it, and that's the end result. What you get is like to oversimplify it. We had to fit the slide. That's why. Okay, let's go back to more serious things. Okay, so we ran this one model. It's great. We can run and create models in Java.
That's super cool. But can't we do better? Because for now we've been like squeezing this ONNX runtime in between. Can we not make it even more Java native?
Yeah, but I think you're right. Because, you know, in the beginning, you said that the GPUs are using these programming languages, OpenCL, CUDA, that are like a subset over the C programming language, right? And So we don't need necessarily a native runtime to translate this thing for us. I mean, because it's ONNX model, ONNX runtime, it's easier and faster to connect to that, and it's less codes and so on. But sometimes we can just interact with the GPU ourselves. And there's another part that we can use when it comes to interacting with the GPUs. And you have made a very nice chart here.
It's true.
This one.
Anna Maria is going to tell a lot about kernels. And when you think about kernels, probably not about seeds, but probably about this operating system core kernel. That's not the kernel we're going to talk about today. There's also machine learning kernels that help you map some data to a higher dimension to categorize it more easily. But that's also not the one. We are talking about compute kernels for the GPU. And that's as much as a compute kernel is a small function that can run on one of these GPU cores, and then it will be run in parallel, the same little kernel on all the cores of the GPU.
So to summarize, kernel is a function that GPU understands. That's how I know it. Okay, so earlier we saw JExtract did some work for us. And since we're still talking about C, and C is native, right? It's native to our hardware. What our colleagues that are working on the second part of the project, Babylon, did was actually to bridge to vendor native runtimes without writing or building native code. So instead what they did, they pointed JExtract to OpenCL, to CUDA, header libraries, and they generated Java libraries, pretty much what we did with JExtract and ONNX, but now at the level of the hardware. And memory layouts, as in our case, allows to express the structured data and so on and so forth. And on top of that, it would be good, we could bind to any backend, right? So, because, you said that there are a lot of offerings up there in the world about different devices that are having their own programming language, and we don't want to install a different JDK just because we're going to run on a different GPU, right? Yeah. So it would be good if we can just swap them. And that's these devices that run these different types of native frameworks. They're called heterogeneous devices, hence why we have the Heterogeneous Accelerator Toolkit. And it's a toolkit because it does a lot of things.
Hey, but Anna Maria, why is Java there between GPU backends?
That's a good question. Well, actually, Java there is because sometimes you need to debug your programs that you're writing, and debugging needs to be provided somehow. So that's why the toolkit, that's why it's called a toolkit. It provides you not only a way to interface with the GPU, it's a library that interfaces you with the GPU, but it allows you to also debug that. So we are and more tools are coming, by the way.
And the very nice trick they use for this Java backend is to just send what you would send to different cores, but to different threads. So you can actually check what would happen on your GPU.
That's pretty cool.
Smart guys.
Yeah, definitely. So in a nutshell, what does HAT offer? Because for me, it's very difficult to say Heterogeneous Accelerator Toolkit. So it offers a way of programming, a style of programming that is familiar to most of the time to the GPU developers. But I think that everybody in this room is Java developer, and if you're a GPU developer, that's great. This is going to be nice. It's looking similar to that. But what it in the end gives us is a library that has a good compute programming model that is working in Java, but it's also aiming to help us minimize our interface with the actual hardware. So it's not just writing Java code, run it on GPU and hope it works well, but it works in a performant way on the GPU, and that's very important. Another great thing about it is it offers us a pluggable backend part. So if I'm running now on my Mac, I'm going to use probably OpenCL because I have an integrated GPU. But if I would have an NVIDIA GPU, I could run just swapping with a different backend for CUDA. And that's really, really neat in terms of that. And sometimes, you can even deploy remote because we have heard that there are GPU in the cloud. So that's not all in the same machine. So even you can, in the remote part, you can deploy it. But there's another catch when working with the GPUs. Us in Java, we use some data types. the GPUs don't speak the same data types as us in Java. So what HAT is offering as one last thing are the interface mapped data types. So a way that you don't need to think about or like struggle with mapping the data type that you have in Java with the data type that you have on the GPU. So it offers all of that. So if I'd like to look again at what happens over there, this is a HAT version of trivial OpenCL kernel function, trivial OpenCL function that squares each element in an array. And if you're looking at this, you're going to say, what's that kernel context? What's that S32R? This is not Java, but it's Java. So what this does is actually creating, via code reflection, an annotated kernel method using the interface map S32R to actually compute on the GPU the square value of the values in an array. Normally, you would do this in Java with an int, right, to compute that. But we're doing this because we want to talk directly to the GPU. And our code is going to go through the same steps as with the ONNX, but just to a different location. It's going to get the code reflection is going to get our input code, is going to generate the code model at compile time, then it's going to lower our model to something that is understandable by the GPU in the end.
Right, so it looks harder, but actually if you would really have to deal with all the GPU things, it would be even harder. So we thank our colleagues that they made these objects available. They look a bit hard, but if we just go with them, we're sure that we're like GPU compatible.
Yep. So the programming model of HAT has a few things. First of all, it has a kernel code. And the kernel code is the code that actually interacts with the function that is on your GPU. That's what you're going to, it's going to be what the GPU gets, so to speak. But you're also having some logic, right, in your programs normally. You have like an algorithmic logic and so on and so forth. So you have a part of compute code. The compute code is the one that dispatches to the kernel what it wants to be executed on the kernel. And in the end, the third part is the accelerator. So the accelerator is the one that is searching for a suitable backend to run all this. So when you're writing the code for this, the main would be having an accelerator first that finds the backend that is available there. Can be your integrated GPU, your remote GPU, whatever. And they says, hey, compute this for me, which is a great thing for machine learning, especially. So what we can look more in detail is like for the demo for this, we wanted to use the Viola-Jones object detection framework. We're not going to use that picture, though. So what this framework does is a facial recognition model, but we're going to run it directly on GPU with no runtime in between, no ONNX runtime in between. So what this model does, it searches for some features in a cascade way, in a tree. It searches first for the eyes. If it finds the eyes, it's going to try to search for, let's say, the mouth, and then it just somehow assumes that we're always smiling.
Yeah.
And we're happy.
An optimistic algorithm.
Now, if at any step in the tree there's a fail, then that is not going to be considered a phase by it. This model that we're going to show today is a very simplified model of what your cameras are using, because probably you've seen the squares on the cameras when you're using the portrait, like, hey, I found a human face. They're using something more advanced than this Viola-Jones machine learning object detection framework. This was patented in 2001. We're running like a very simplified version of it, but it's pretty nice to see his output. So let's see for the very last part. We have the demo. Yes. Yeah, play. So HAT is inside the Babylon build, and it builds as a library. At the moment, it builds on top of Babylon. What this means is that to build it, you actually, I don't have it here. You actually need to like point to it, the JExtract home. It needs JExtract for it to work. JExtract home. So you need JExtract on your local if you want to build HAT. And then you have to do something like Java at HAT BLD.
So on top of building the Babylon JDK, you also have to build HAT.
Yeah.
if you want to run this. But it's all described in the README if you want to try it at home.
Or you can just put us to do that in, after this and just show me again. Delete all your things and then show me again. I can do that. It's no problem. And if you're thinking that this Java hat BLD is like sounding very weird, well, our colleagues used something called argument files just to dump all their commands in an argument file, and it looks neater when you're using this for a library at least. Okay, but I said I want to do Viola Jones and to do a facial recognition, run a facial recognition model on a picture. So I have here my main that reads a picture from somewhere, and then it's going to use hard cascade model, so it's going to do that tree based on an XML definition. So that is going to be loaded from XML, the tree itself, but the tree is going to be instantiated and used in the actual core compute. And if I'm looking at this, core compute, what it does, it has multiple methods. It has one method for compute, but it uses multiple kernels because in the tree that you have there, you want to be able to execute that each identification feature part, you want to send it to the kernel and to execute it and then go to the next one, but you can do that in one compute. So let's run the example because that's much more interesting. First of all, Java run hat run. Oh yeah, I don't have I don't have NVIDIA. I wish I had NVIDIA.
Yep.
And OpenCL Viola Jones. You can also see what it actually runs. Wow.
That was fast.
Okay, too fast. Even for a slow Mac. Anyway, I think it's Mac. What it worked is like it got me all so that has like 92 faces in 104 milliseconds. That was really, really fast. So you can where you know the faces are. The faces are like where multiple squares are around. There are some misses, of course, like it interprets like some wrinkles in somebody's pants that, well, might be some face there or like a beginning of a face or a nose or whatever. It is late. And then you can see that there's a miss on Ron, the fact that his face was not captured. This model, this is, as said, is a very simplified machine learning model. We try to simplify as much as possible. It doesn't recognize faces that are tilted. It searches for kind of straight eyes. If it's tilted too much, it's going to be like, hey.
You cannot be too enthusiastic on the picture.
Yes, you have to be like more like me. Like I said, express my happiness in the Eastern European way. Anyway, so yeah. This is the signal you that's going to be at Java 1 in 2026 if you want to join, and more sessions are going to happen there. But what I want to show, and actually it's more excited than that, is that hat is providing a few ways to look at what's actually going on under the hood.
Yeah, because for now it's been a bit of a black box, right? We believe that code reflection does cool stuff.
Yeah.
But what has actually happened?
Okay, because I kind of forgot some stuff. Okay, so if you're curious on what exactly is executed on the GPU, we have this info equals showcode, and we can do Java at hat run. I should have put this in the front of everything. OpenCL Viola Jones. Yes. So what this is going to say, it's going to print for you in this lovely output here. It's going to log what code, OpenCL code, lovely OpenCL code is going to be executed. In case you're like wanting to run the same thing directly on the... Okay, come on. It worked earlier. That's why I have a README. Hat, shortcode. Oh, no, it's late. Come on. Clear? See? I said info because I was thinking it's something else. It should have been hat because the features are in hat, obviously. I was going to do better. So this is the OpenCL code. If anybody's interested to run this directly on the GPU, good luck, have fun, enjoy. No, I'm not interested to run that on the GPU directly. It's too late for that. Okay, but what else? We're interested to see like what that code reflection thing is there generated, and maybe look at the compute model that is available So what does the code reflected model when it goes to the compute method? So I'm going to say show compute model code. So this is like for debugging especially, this is very useful because you can see all the steps that your project is going through, and it's quite neat.
So this is what code reflection translated to.
Yes. Very interesting and understand. It's kind of like in between Java and the foreign part.
I think this is just a great thing to send people home with.
Yeah. Well, the last part that I want to share actually. Now, Viola Jones is a machine learning model that is using multiple kernels. But there are cases when the machine learning is using multiple compute methods. So it may use one kernel and multiple compute methods. So in the case that is using multiple compute methods, there's another option that's called minimize copies. Now, in our case, it's not going to do much of improvement from before because it's a kernel-intensive model. But for Game of Life or other examples that are there, try to use minimize copies. What this will do, it will try to tell the CPU, and we'll try to tell the GPU through our code, like, do not do that many returns and go back and forth towards the actual hardware. So optimizes the copies that you are doing when you are going to the hardware before actually hitting that hardware. It is very useful to do.
We had 92 seconds instead of 103, so we got it down a little bit.
And we had to allow down a little bit, but for like a Game of Life, which is a little bit more intensive in computation, let's see. But this is a very slow laptop. Okay, Life. Let's see. Yeah, this is Game of Life running on my computer. Very slow. Oh, I have to say start. Details. So yeah, it's pretty much going quite well and generating some stuff, but you still have to wait a lot. If you want to see it, a Game of Life in a faster mode, tomorrow go to Paul Sandoz' talk. He has a better laptop, so he can run it faster than me.
So now you see the digital clock actually appearing on the bottom. It's kind of a computer made of Game of Life objects.
Yes, pretty cool. Okay, let me exit on this one and go back to our last slides. We're going to share the slides with everyone. Don't worry. We are waiting for your questions. You can get to meet more awesome people that are working on OpenJDK at Java 1 next year in 2026 and ask them more what they're going to do for the evolution of Java for AI. But until then, there are a few other talks that you can watch at DevOps tomorrow. Yeah. One, I think at 9:30 in the morning, I know, quite early. Java for AI by Paul Sandoz. It's going to be a little bit more digestible, I think, than what we shared today, but we hope you enjoyed it. And there's another one, which is very...
Yeah, Adam Sotona, who's going to do similar things than us, but then with GenAI, ONNX Runtime's GenAI, and working with LLMs, manipulating them in Java directly.
So pretty much just using generative AI models. We use the machine learning, which was a little bit easier and smaller scale that you saw today. But his demos are the next level, because everybody's about GenAI these days, right? And we want to talk to a chatbot and run it directly in Java, if possible.
Okay, with that, we're going to let you go home. If you have questions, just come meet us here. We're happy to show you anything else.
Yes, we're having more things to run on our laptops. Or meet us at the booth. We're at the Oracle booth, so you can also address questions to us there. Paul Sandoz is going to be there from time to time as well. So yes, definitely more smart people will be there to answer your questions. But I hope you enjoyed it and that you saw what is possible to do in pure Java in order to talk and to optimize your runs directly on the GPU and make things even faster. I think it's a nice progress.
Okay.
Thank you.
Thank you.